Dr. Beck, and this video is on intermolecular forces. In this video, I hope you'll learn to be able to describe the 5 different basic types of interactions between atoms, that you'll be able to predict the relative strength of interactions based upon those different types, and that you'll be able to use those strengths of interactions to then be able to predict physical properties of atoms and molecules. Before you watch this video, I encourage you to be comfortable with Coulomb's law, kinetic energy, and states of matter. If you're not comfortable with those, I encourage you to watch a video or learn about them from your book. Intermolecular interactions will be the interactions between 2 adjacent water molecules, for instance, shown here. Intramolecular interactions will be bonds, only bonds between atoms within a molecule. So here we're only worried about interactions between molecules, and those are going to be having different types of interactions. We'll try to classify those and use that to make predictions. Okay, one of the things that we'll want to do is be able to visualize or have some understanding of what these atoms might be looking like. And this is a nice simulation from PhET, which gives some idea of how these interactions look on a molecular behavior. Here we're showing a solid, in this case neon. And it's a solid, so it has a fixed volume and has a fixed shape. You may notice some important things. So first, this is very cold, so 13 degrees Kelvin. And also that the molecules, although they are next to each other within a solid, that they still have motion, and motion means kinetic energy. And the key thing that we're going to be looking at today is this conflict between the kinetic energy, where something is able to move, and the force or the intermolecular bond that's holding that together. And this is the constant competition. So as we raise the amount of kinetic energy, so we raise the temperature up to 26 Kelvin, now we have a liquid, so something which has bonds between atoms, but these are able to change. You're able to have bonds exchange bonds with atoms that are adjacent to them. And we go to a gas, in this case for neon at 55 Kelvin. Now we have the kinetic energy, which is much greater and overcomes all of the bond energy that could hold it together. And this is the basic concept that we want to have. That we want to have this idea that there are 2 influences on the state. So one is the kinetic energy. Our measure is going to be temperature. So as we increase the temperature, we increase the kinetic energy. Here the kinetic energy of molecules, and this is in balance or conflict with the electrostatic interactions or our intermolecular interactions. And these are based solely upon Coulomb's law. So this is just charge interactions. If we have more charge or a shorter distance, it'll be a stronger interaction. And this is what we're going to use to be able to make predictions about the strengths of interactions. And for us, we're going to use this strength of interaction to make predictions about state, and vice versa. So state and temperature are things that are going to be important. The state informs us of the interaction strength. So something that is a solid at room temperature must have very strong interactions. So there's a lot of kinetic energy there, but that's being overcome by that strength of interaction. And vice versa. So something that has strong interactions is most likely going to be a solid at room temperature. So we'll use these in 2 different ways to try to make predictions about state or about strength of interaction. Okay, looking at the solid again in the PhET demonstration, that we see that here the kinetic energy is not enough to overcome that bond energy. And in the gas, we'll see the opposite. We'll see that the kinetic energy is more than enough to overcome that intermolecular bond energy. So we can look at this in terms of kinetic energy diagrams. So remember that at a particular temperature, the kinetic energy of any molecule is going to be a distribution across some spectrum. So we'll have an average or root mean square or maximum point. We'll have some way of describing that energy, that kinetic energy of molecules. And for us, when the intermolecular bond energy is much greater than the kinetic energy that the molecules possess, this will be a solid. So the kinetic energy is not enough to break out and tear away from the intermolecular interactions. So this has some energy still, is jiggling, but it's held in a solid state, so its interactions are maintained with the molecules that are adjacent to it. Conversely, that when we have an intermolecular bond energy that is much less than the kinetic energy, that this there breaks all of these bonds, and we end up with something that's a gas. And a liquid is going to be something in between. So our view of kinetic energy or temperature and state can be based upon the interaction between the kinetic energy and intermolecular bond strength. Okay, let's look at bond strengths in general. So we'll briefly take a look at 5. You should be comfortable with a couple of these already. So roughly in order of strength, covalent bonds are stronger than ionic bonds, and hydrogen bonds would be the next strongest, followed by dipole-dipole and London dispersion forces. And we'll go into all of these in just a minute, but an important point that you can have more than one or combinations of these that can happen at the same time. Covalent bond is really a sharing of electrons. So here I'm showing my water molecule, which has some unbound electrons indicated by these two clouds on top, and bound electrons, electrons that are shared indicated by this bar in the middle. There's a very strong interaction, and we can measure the bond energy, how much energy it costs to break those bonds, and it'll be in hundreds to thousands of kilojoules per mole. A very strong interaction. And we know it's a strong interaction because these things do not fall apart at room temperature. So we have water molecule, we can boil it, we can turn it up to very high temperatures, and it does not break those bonds. Those bonds hold together even at very high temperatures. The next strongest interaction will be ionic bonding. So as we have molecules that have atoms that have transferred electrons from one atom to another, so our sodium chloride, for instance, we now have a strong positive charge and strong negative charge, and that's attracted to each other, and it'll form this characteristic crystal structure. And we know this is a very strong interaction because these are salts. And salts at room temperature, pure salts, are solids. So we know sodium chloride is a solid at room temperature, which means those interactions must be very strong. We can heat it up and melt it and boil it, and we can turn those into gases, so it's not as strong as a covalent bond. There's a very strong interaction that allows it to be a solid at room temperature. Okay, the third type of interaction is based off of dipoles. So you may recall we take a look at, for instance, the water molecule, that this is a polar molecule. So I have 2 electrons on this side, and I have hydrogen. The oxygen in the middle is drawing those electrons to itself. I end up having a positive charge on the end of my hydrogen atoms and negative charge that's around the oxygen. So I have a dipole moment. So we're going to take 2 of these molecules that have dipole moments, say PCl3 shown here. They will arrange themselves, not surprisingly, so the positive sides will orient with the negative sides. And in PCl3, my chlorine is going to be more negative. So my negative charge here on the surface will align with my positive charge. And remember, these are surface charges. So if we looked at the surfaces of these atoms, we would see there would be slightly more electrons hanging out on the chlorine side and slightly fewer hanging out on the phosphorus side of the adjacent molecule. And so these will arrange themselves so these positive and negative charges interact. This is not quite as strong as a full electron being transferred, but still it's a charge distribution, so it's a charge-charge interaction. Fourth type of interaction is hydrogen bonding. This is a subset of dipole-dipole bonding. This is a specialized dipole-dipole. This only happens when you have hydrogen that's bound to nitrogen, oxygen, or fluorine. We call them the NOF group. And this is stronger than other dipole-dipole interactions. And that's why it's given the special name of hydrogen bonding. We can observe that it's stronger than other interactions because the boiling point for something like water, which exhibits hydrogen-hydrogen bonding, and is higher than the boiling point of something such as PCl3, much higher than the boiling point of PCl3, which doesn't exhibit hydrogen bonding. We can take a look at what this looks like. So if we go to a hydrogen molecule, here are my 2 hydrogen atoms. So this is the same idea as a dipole-dipole. On the surface, there's going to be a charge distribution, and those positive charges, in this case at the hydrogen terminal, align with the negative charges, in this case from the oxygen side. This is my hydrogen bonding. This is very strong bonding. So one of the reasons it's very strong is that oxygen, nitrogen, and fluorine are very electronegative, so they're very good at drawing electrons to themselves. Second reason is that they're drawing those electrons away from hydrogen. So as the electrons get drawn towards the oxygen side of hydrogen, they spend less time out on the hydrogen side away from the oxygen, and we're left with no electrons, so we essentially have an exposed proton that's on the surface of these water molecules. And that exposed proton is going to be very strongly interacting with other things, including the highly electronegative oxygen atoms. So remember that all my other atoms are going to have inner shells of electrons. So all my other atoms are going to be shielded in some way from that proton. So that proton in the nucleus in hydrogen, when it's bound to something very electronegative, gets much more exposed, and that creates a much stronger bonding. So it's a very unique circumstance, and it's given this extra name of hydrogen bonding. Okay, lastly, the last type of interaction that we'll come across is London dispersion forces. So London dispersion forces only are dominant in small molecules when you have no hydrogen bonding, you have no dipole-dipole, and you have no ionic interactions. And London dispersion forces can happen when you have this cloud of electrons, and it's easiest for me to think of these as a bag of electrons that's on the surface of two molecules. And as those electrons start moving around, you may find from time to time that those electrons find themselves on one side of the atom versus another. So here I have my electrons that have arranged themselves in a neutral atom. So a nonpolar atom is arranged, the electrons just happen to be on one side. This creates a positive side and can influence the molecules next to them. So as London dispersion forces is sort of a sloshing of the electrons from one side of a molecule to the other by accident, and this can happen randomly. And if it happens for a long enough period of time, then it can sit next to an adjacent molecule and influence that adjacent molecule, and you'll get this charge distribution on a neutral molecule that then you have sort of a dipole-dipole interaction. We'll call this an induced dipole. So a couple of important things for this. So London dispersion forces on small molecules, things have to be moving pretty slowly for this to happen. So if the London dispersion forces are the only thing that are influencing the interactions, this must happen at a low temperature. And we observe this. So if we look at the boiling point of neon, which we just looked at, find it's 27 degrees, right? So to break those interactions is very easy. It's a very low temperature. It just takes a little bit of kinetic energy to break those London dispersion forces. If we look at something like xenon, we'll see that the London dispersion forces in xenon are much stronger. And we can observe this in the boiling point is 165 Kelvin. So we compare neon and xenon. Both of these are noble gases. Neon's very small, xenon's much bigger. They can only exhibit London dispersion forces, and they have vastly different boiling points. So size is important. As we get electrons that are further away from the nucleus, it's easier for them to slosh from one side to the other, and so you're able to form stronger London dispersion forces, and as a consequence, the boiling point will be higher, the physical characteristics of the substance will be different. If we look at a molecule, say methane, we'll see that it has a boiling point of about 109 Kelvin. If we compare that to ethane, that'll be 184 Kelvin. So the boiling point for ethane is higher. These two molecules, they don't differ in radius, they just differ in length. So ethane is a longer molecule, it's just like two methanes stuck together. Ethane is a longer molecule, so it has more surface area, has more electrons, and is a better chance for those to be able to slosh from one side to the other, and we observe a higher boiling point. So London dispersion forces can add up to be very strong forces, and you can have things like gasoline, which is a very long hydrocarbon, instead of very long hydrocarbons, and this is a liquid at room temperature, so it must have very strong interactions, even though it has no polarity and obviously no ionic compounds. So in general, we'll get stronger London dispersion forces when the surface electrons are further away, so on larger molecules. And we have a larger surface area, so when there's more places for those electrons to hang out, we'll get a better chance that they'll shift from one side to the other. First question, so which compound will have a higher boiling point? CF4, carbon tetrafluoride, or difluoromethane? Well, the first thing I want to do with these questions is figure out what are they asking in terms of interaction strength. So which one will have a higher boiling point? So they're asking which one has a higher strength of interaction, has stronger forces holding it together so it can withstand higher temperatures before it breaks apart into a gas phase. So they're asking which one is going to have stronger interactions. I'll look at CF4. This is going to take a tetrahedral shape. It's going to be a nonpolar molecule. And I'll look at the difluoromethane and see that it's a polar molecule, so I can have dipole-dipole interactions. There's no hydrogen bonding because I don't have a nitrogen, oxygen, or fluorine. There's just some dipole-dipole interactions. CF4 is a small molecule. It can only have London dispersion forces. I predict that the dipole-dipole interactions will be stronger than the small London dispersion forces. And in fact, this is what we observe. So difluoromethane does have the higher boiling point. Second question, which compound will have the lower melting point? First step I want to do is figure out what are they asking here. So they're asking me which one of these compounds is going to have the weaker interactions. Lower melting point means it will break those interactions in the solid earlier at a lower temperature, which means it will have weaker interactions. So they're asking me which one of these has weaker interactions. I'll look at these two. I have ethane C2H6 and butane C4H10. These are the same hydrocarbon structures. One is longer than the other. And from earlier, you may recall that the longer hydrocarbons, the longer molecules, will have higher dispersion forces, have more opportunity for the electrons to shift from one side to another, so stronger interactions due to London dispersion forces. So I would predict the ethane has weaker forces and therefore the lower melting point. Third question would be a question, which compound will boil at a lower temperature, butane or methanol? So here I have, again, butane, which is a little bit longer hydrocarbon, so it has stronger London dispersion forces. Methanol, notice that I'll have an OH group, so this is going to be similar to water. I'll have hydrogen bonding that can occur between the oxygen and the hydrogen. Again, what are they asking? Which will boil at a lower temperature, so which one they're asking, which one will have the lower strength of interaction? The methanol is going to have a stronger strength of interaction due to hydrogen bonding. It will be much stronger than the London dispersion forces that happen in butane. And again, this is what we observe. So can you now describe the 5 basic different types of interactions between atoms? Will you be able to use these to predict the relative strengths of interactions? And will you be able to use those relative strengths of interactions to predict physical properties? I hope you can.